Okay, in this video, I'm going to be talking about implicit differentiation, and this is the first lesson in Unit 4 of CalBC. All right, now at the beginning of this course, we took derivatives of things like what you see there, like sine x and x to the third plus 4x minus 5, or 1 minus the third root of x. And it turned out that we'd been doing the chain rule the whole time once we learned the chain rule, right? Because the derivative of the inside was just always 1. But then, once we learned the chain rule, we were able to expand our library of functions we could take the derivative of, like those, where, the derivative of the inside of the function was not necessarily just x, or the derivative wasn't 1, or the inside wasn't only x. Now what we're going to do is we're going to look at implicitly defined curves, which are honestly much more interesting. Notice how these are all y equals and then a string of things involving x. Well, what if we had something, like y squared e minus sine 2x equaling 1, or e to the y equals the square root of, x minus 5, or the natural log of y times the third root of 1 minus x equals 0. I don't know, something like that. Okay. These are the type of things that we're going to be needing to take the derivative of now. These are equations that are implicit, where x and y are allowed to roam freely. Okay, so first I'll show you a couple of, or 4 equations that, you've seen at some point up to now. Anybody know about the blue one, x equals y squared? What does that look like? Yeah, okay, it would kind of look like y equals square root x. It's a sideways parabola. Yeah, so, it kind of looks like that. X squared plus y squared equals 1. You all know this one, whether or not you know what it actually is. We know what it is. Not just any circle, it's the unit circle, yeah. Yeah, registered trademark, whatever. You spent the entire first half of last year probably, or for some of y'all the year before last, studying the unit circle, right? Now, x squared minus y squared equals 1. Anybody remember this one? It is, yes. It's a hyperbola. I don't know who you were that said that, but you're right. This is actually the unit hyperbola, and much like how the unit circle is where we would get trig functions from, the unit hyperbola is where we would get hyperbolic trig functions from. Unfortunately, hyperbolic trig is not part of our course description, and therefore it won't be part of this class or this video. All right, and then ax squared plus by squared equals 1. That's just where if a and b are different, then that could be where, yeah, it's going to be an ellipse. It's like a circle that got somehow out of proportion. Okay, yeah. These are all implicitly defined curves and things that we might want to find the slope of a tangent line. So kind of like, just stating our purpose here, like today we're looking at the slopes of curves that are defined implicitly. We're going to call it implicit differentiation. And really what this is a vehicle for us to practice our derivative rules, really, and to, kind of investigate the chain rule a little deeper. But the deal is the chain rule is the basis for what we're doing here. All of the problems that we're going to do, we're going to have to be considering the chain rule. Now, you're going to say, well, wait a second, this equation is not defined implicitly, and no, it's not. It's y equals a function of x. But it's a function that I kept seeing over and over again in the last unit, in like the multiple choice packet and stuff like that. And, it's never a bad time to practice the quotient rule. So what I'm going to, just remind you of is the fact that if two things are equal, then their derivatives are equal. We can take the derivative of both sides of the equation with respect to x, and it will preserve the equality. All right, and we know how to use the quotient rule. Bottom, derivative of top. What is the derivative of natural log? 1 over x, good. Minus the top times the derivative of the bottom is 1 divided by the bottom squared. Okay, and if we had to do something else with this, we would probably want to just call this 1 minus the log of x divided by x squared. All right, now, I want y'all to take the derivative of this thing using the chain rule. Okay, remember how to do that. I'm not going to tell you what f of x is because, you know, I'm trying to make a point. If you got the note packet in front of you, you can see what, you know, a little bit below what that's going to look like. Take the derivative of f of x squared with respect to x. Okay, if you're watching at home, pause the video because the answer is just going to pop up. All right, so there it is. So remember that when we take the derivative of a thing that's squared, it's 2 times that thing to the first. But sometimes that thing has its own derivative that we have to account for using the chain rule, right? That's where the times f prime of x comes in. Now, we're going to do the same thing, except instead of calling it f of x, we're going to call it y. Okay? So we know how to take the derivative of a thing that's squared. It's going to be 2 times that thing to the first power, and then I'm going to need to multiply by the derivative of y. Now, what is the derivative of y with respect to x? Yes, you could say that. Or, yeah, or dy dx. Okay, I'll say I'm always going to use dy dx because coming sooner than you imagine, we're going to be separating dy and dx. And so it's I think, and I prefer that notation. It calls back more to what we're doing when we're taking a derivative. We're taking the limit of rise over run as run goes to 0. Okay, so it's 2y dy dx. All right, next one, the derivative with respect to t of 3x to the 4th. Now, what would you think the derivative of 3x to the 4th would be? 12x to the 3rd, yes. Okay, wonderful. But it's possible that x is a function that depends on t. In the last unit, we looked at particle motion problems where it was particle moving along a line, and x was some function of t. X was the position. So it's not out of the realm of possibility for x to depend on time, or t, or some other variable, right? So the x could be the inside of this function that might have its own derivative with respect to t. So we multiply by dx dt. If x and t were the same thing, well, then dx dt would just be 1, and we would still be, you know, saying something that was true. Okay. And what you'll see when you start thinking about it is that you've been doing implicit differentiation the whole time. You take the derivative of something with respect to x, because the derivative of x with respect to x, well, what is the derivative of x with respect to x? 1. Yeah, it's 1. It's dx dx. That just sounds like 1, doesn't it? Okay, so, you know, that's the thought process. Okay, so now I'm going to give you a few to look at and maybe try on your own. All right, so these are 4 that I would like for you to try on your own. Okay, don't forget to multiply by the derivative of the inside when you need to do that. When you're taking the derivative of y with respect to x, you need to remember that dy dx. Okay, if you're watching at home, again, you need to pause the video because the answer is just going to come up in a few seconds.
Is that 6y?
Yes, that is 6y.
Oh.
Okay, there they are. And, okay, the first one. Okay, I take the derivative of the outside. So I take the derivative of sine of a thing, and that's cosine of the same thing. Leave the inside the same. Then multiply by the derivative of the inside, which was dy dx. Oh, I see I've made an error. Anybody see the error in the picture? Yes, back there, 100. Yes, it is the second one. And what are you seeing? Yes, I put dx instead of dt. Okay, yeah. And so remember, you have to be very careful about what variable you're taking the derivative with respect to. All right, so there it is. Let me just. So with the third one, this is a product situation. So I do apply the product rule. So I start by taking the derivative of x with respect to x, which is just 1, leaving e to the y to the same, and then leaving x the same and taking the derivative of e to the y. Well, the derivative of e to a thing, 139, is e to the thing, right? Times the derivative of the inside. Okay, and the derivative of y is dy dx. See what I'm saying? Did that answer your... All right, and the last one I have where we're just going to take the derivative of an expression is the derivative of x times y. And this one is going to show up all the time. It's on, if you look at your multiple choice packet, it's all over the place. If you look at the free responses that are implicit differentiation related, there's lots of x times y. College Board seems to really like this example. So I'm trying to, stress its importance. So what I'll do is I'll go over here and I'll say, well, this is a product rule situation. I'll take the derivative of x with respect to x. That is, yes, 1, leave y the same. Then I'm going to leave x the same, and I'm going to multiply by the derivative of y, which is dy dx in this case, because I'm taking the derivative with respect to x. Okay, so that's y plus x dy dx. Honestly, I don't recommend that you try to just remember this for all the times that it comes up, because if you just, give a faithful effort on the product rule, it will help you recognize when there are product rule situations. Which it seems like this year there's been, some people have had an issue not administering the product rule, but recognizing when it's a product rule situation, especially when it's not so obvious. Yes, sir?
Will it ever be yx?
Yes, it could be yx. It seems like stylistically, they will, when they multiply two variables, they put the, they go alphabetical order. So it'd be like, even if it's x to the third, y to the second, or x to the second, y to the, they seem to always put x before y, but it is certainly possible. And then you would probably, if you're like me and you always pretty much take the derivative of the thing on the left first, you'd end up with x dy dx plus y. But we know that, 10 plus 2 is the same as 2 plus 10, so it doesn't really matter. All right, so we've taken the derivative of expressions, but not really like equations. And, at the beginning, I promised you we were going to look at implicitly defined curves and find their slopes. So we need an equation for a curve. And there's kind of a set of steps for finding dy dx on implicitly defined curves. Now, the first step is going to be to take the derivative of both sides of the equation with respect to x. Then we're going to, we're going to have an equation that's going to have some dy dx's in it because, it's implicitly defined. So there's going to be a y in there, and that'll cause there to be a dy dx. And we're going to move all of the things with dy dx to one side of the equation while clearing everything else out to the other. Okay, then after that, we're going to factor out the dy dx. And then we'll solve for dy dx by using division, dividing. All right, so let's actually, put this into action and find dy dx on some implicitly defined curve. All right, so here we have it, a curve that's defined implicitly. I feel like I don't know what the graph of this thing looks like. If you're interested in what any of these things look like, you can, kind of just type them into Wolfram Alpha, and it'll show you a graph. And some of these are really interesting. I'm not sure what this would look like. I don't know how that minus xy is going to play in with the x squared plus y squared, because x squared plus y squared equals 10 is just a circle. So I don't really know what's going to happen with this. But regardless, we just want dy dx. We don't even have to worry about that. What we're going to do, we're going to start by taking the derivative of both sides with respect to x. So the derivative of x squared is 2x. Okay, minus, and I'm going to just, kind of hold that minus sign out in front and then just take the derivative of xy. If you want to do the product rule with negative x and positive y, you'll get the same thing. Okay, I just don't want to make an error. Okay, so I'm going to take the derivative of x and leave y the same, then add in, leaving x the same and taking the derivative of y. Then plus 2y, but y has its own derivative. And the derivative of 10, that's going to be 0. So I'm going to distribute the negative real quick. Okay, now I'm going to move all of the things with dy dx to one side of the equation. Okay, well, they're both already on the left side of the equation, so I'll just clear out all the rest of the things. So I'll just say that's equal to y minus 2x. I've still got this negative x dy dx and 2y dy dx. Okay, then I'm going to factor out the dy dx. And then I'm going to solve for dy dx by dividing away the thing it's multiplied by. And that's dy dx. So before, yeah, so in this, if you had a point that was on the graph of that equation, say where x was 0 and y was, I guess, the square root of 10. Okay, you could find the slope by plugging x equals 0 and y equals the square root of 10 into the formula for dy dx, and I do believe that that would give you 1/2. Okay, so that's one thing you could use it for. We're going to write the equation of a tangent line, I expect, pretty soon. But before we move on, I'm going to kind of reconcile this with a set of steps I've listed up above just a minute ago. So first, I took the derivative with respect to x. Then I gathered all the terms involving a dy dx to one side of the equation while clearing out the other ones. Then I factored out a dy dx, and then I solved for dy dx by dividing. And pretty much it's going to work like this every time. So I think at this point we just need to do a bunch more examples. All right, so here I've got one for y'all to try on your own. Okay, so take the derivative of x squared plus y squared equals 1. And I'm going to freeze the video or freeze the screen for y'all in class. I'm going to pause the video recording. So if you're watching at home, you need to pause. All right, there you go. So this, this example is mostly pretty friendly, but I've kind of got, like a point to make with this. I'm going to attempt to draw you x squared plus y squared equals 1. I canceled the 2's, but if you didn't, it's not a big deal. All right, this is a unit circle. And the point I'm making is really valid for any circle, right? Because when we took the derivative of 1, it came back 0. Think about a radius. Okay, it's a radius to the point x and y. Well, what is the slope of that radius? Yeah, y over x, okay? But what we just saw was that the derivative, or the slope of the tangent line, was negative x over y. And something that they may have told you in geometry class, this is a horrible drawing, was that a tangent to a circle is perpendicular to the radius at the point of tangency. And notice how, something bad happened there. Notice how, it kind of looks pretty perpendicular. And if we take the slope of the gray line, which is y over x, and we multiply it by dy dx, we'd get -1, which is indicative of two things that are perpendicular. All right, yeah, now let's actually use dy dx for something. Okay? We need to write an equation for the line tangent to the graph of x to the 2 minus 3xy equals 10 at the point 1, -3. Yeah, we can do that. Okay, well, we've got a point. Now what we need is a slope. So what we're going to do is find dy dx, and then we'll plug in x equals 1 and y equals -3. We'll have a slope, and then we can write the equation. It'll be great. So I'm going to start by taking the derivative of both sides with respect to x. I'm going to hold the -3 out and take the derivative of xy. Right. Now I'm going to, I'm probably going to move the 3y and the 2x, but if you wanted to just add 3x to both sides, maybe I will do that. It's not what I would usually do, but whatever. I'm going to solve for dy dx by dividing both sides by 3x. Right, so now that I've got dy dx, I should be interested in what the value of dy dx is at the point 1, negative 3. All right, well, I'm going to plug in x equals 1 and y equals negative 3, so it'll be 2 plus 9 is 11 over 3 times 1 is 3. So I got 11 thirds. Now I'm going to say I've got a point and a slope, so I'm ready to write the equation. Y plus 3, y minus negative 3 is equal to 11 thirds of x minus 1. All right, now let's look at horizontal and vertical tangent lines. And I guess before we do this problem, we need to kind of talk about what does horizontal and vertical even mean. All right, in terms of rise over run, horizontal is where it's running but not rising. So rise would be 0, run would be something. That's dy dx equals 0. And since in this situation dy dx is generally a fraction, we're looking for where the numerator is 0 while the denominator is non-zero. The thing is, though, in this class, you shouldn't have to worry about what happens when the numerator and the denominator are simultaneously 0. That's not something we're going to deal with. Okay? And then, on the other hand, there's vertical. And a vertical tangent would be where it was rising but not running. So in terms of rise over run, that would be a number divided by 0. And that's undefined. Okay, so dy dx undefined because of division by 0. Okay, now in terms of this question, we're going to need to find dy dx. It's going to be a fraction, and then we'll basically take the numerator and set it equal to 0. We'll take the denominator, set it equal to 0 separately, and then we'll see what's going on. Okay, so let's start by just taking the derivative of both sides of this equation. The derivative of 4x squared is going to be 8x to the first plus 2y dy dx minus 8 plus 4 dy dx plus 0 equals the derivative of 0 is 0. Okay, cool. Now I'm going to clear out anything that doesn't have a dy dx. And maybe I'll also, at the same time, factor out the dy dx. That's how I generally do it when I'm working these problems. I factor it out while in the same step as I push the other stuff to the other side. So I've got a 2y and a plus 4 is equal to 8 minus 8x, meaning that dy dx is equal to 8 minus 8x divided by 2y plus 4. Okay, now, if I'm interested in the horizontal tangent lines, what I'm going to do is I'm going to take, 8 minus 8x, I'm going to find out where that is 0. Okay, well, that's looking to me like any place where x is 1, that will be a horizontal tangent line. So I'll just plug in x equals 1 into the original equation to find, nope, that's not the original equation. All right, yes, the original equation, the actual equation that relates x and y and not x, y, and dy dx is that one. Okay, so I go back to that one, and I plug in 1 for x. So I've got 4 times 1 squared plus y squared minus 8x, so that's minus 8, plus 4y plus 4 equaling 0. And look at that. That's 4 plus 4 is 8, minus 8 is 0. Y squared plus 4y equals 0. Okay, this is the type of thing we should factor. Okay, so now I've got y equals 0, but also y equals 4. So there's 2 points on this curve where x is equal to 1. Oh, yes, I see what you're saying. Definitely negative 4. Thank you. All right, so the coordinates here are x equals 1, y equals 0, because, they're asking for the xy coordinates, and x equals 1, y equals negative 4. Okay, we're happy. Now for the vertical tangents, we're going to do the same process. We're going to go over here, and we're going to look at the denominator and see when is it equal to 0. Okay, Okay, so 2y plus 4 equals 0. That's going to be when y is negative 2. Okay, so I'm going to go and I'm going to plug in negative 2 for y, and I'll have 4x squared plus y squared would be plus 4 minus 8x plus 4y would be minus 8 plus 4 equaling 0. All right, so now I have 4x squared minus 8x equaling 0, which is 4x times x minus 2. And now this thing will equal 0. And this is going to happen where x is 0 and also where x is 2. Okay, so the xy coordinates of the places of the vertical tangent is going to be 0, negative 2, and 2, negative 2. And that's how we deal with these horizontal and vertical tangent problems. All right, here we have one of these problems that's kind of like, I think it's probably modeled after one of the free response questions from an AP exam. Y equals f of x is a curve that satisfies the differential equation. Basically, if you take the derivative of this function, you're going to get the derivative is equal to negative x minus a third of y plus 2. With f of 1 equals 3. Well, the first thing I'm going to tell you is that f of 1 equals 3, that means the point 1, 3 is on the graph of f. Okay? And when they say find the second derivative of y with respect to x both times at the point where x is 1 and y is 3, well, what we're going to do is we're going to take the derivative of dy dx. So what we'll do is we're going to take the derivative of both sides of the equation, just like we did earlier. I'll take the derivative of negative x minus 1/3 of y plus 2. And the derivative of dy dx is the second derivative of y with respect to x both times. Okay, now the derivative of negative x with respect to x is going to be negative 1. Okay. If I were taking the derivative of negative 1/3 of just a thing to the first power, well, with the power rule, that's just negative 1/3. But y might have its own derivative with respect to x, so I'll just put that there. Plus 2, well, the derivative of 2 is 0. Right? Now, the thing is, we could figure out what dy dx was at 1, 3, and then substitute it there. But there are quite a few questions. You'll see it on the homework, it's on the quiz, probably on the test too. If you look at old free response items, they say find the second derivative of y with respect to x both times in terms of x and y only. Okay, so that means that we have to get rid of this thing. Luckily we have a formula for that, so we're just going to plug in and use a set of parentheses and it'll be all right. Okay, and so it's going to be negative 1 minus 1/3 of negative x minus 1/3 y plus 2. All right, so if they ask me to evaluate this second derivative at the point where x is 1 and y is 3, well, that'll be negative 1 minus 1/3 of, negative 1 minus 1/3 of 3 is minus 1 plus 2. Okay, well, that's actually looking like negative 1 minus 1/3 of 0, and that's negative 1. Okay, so the second derivative was negative 1. All right, and then in part B, they're going to ask you, does f have a local maximum, a local minimum, or neither at the point 1, 3, and to justify my answer? Okay, well, as far as local maxima and local minima are concerned, we have the first derivative test and we have the second derivative test. And the first derivative test requires some sort of analysis between the derivative went from positive to negative, but we don't know anything about f of x. So we're not going to be able to do that. So what we have to do is do the second derivative test. So what I'll do is I'll take this and I'll find out what dy dx is. Based on what happened when I substituted on dy dx in part A, I think it's going to come back 0. But, always good to check. dy dx is negative 1 minus 1/3 of 3 plus 2, which is equal to 0. Now, the second derivative in part A, we showed to be negative 1. So I'm going to say, okay, I'm considering the fact that it's flat, while concave down, which means it's hit a local maximum. That is not sufficient justification. You need to use a sentence. Right? So I'm going to say, you know, f takes a local maximum at x equals 1 because f prime of 1 equals 0 and f double prime of 1 is less than 0. All right? Now, if you said dy dx equals 0 and the second derivative of y with respect to x both times is negative, that would work just the same. Okay, that's how we're determining maxima and minima for implicitly defined curves. It's by using the second derivative test, not the first. Okay, I've got another free response question for you. Y equals g of x is a curve that satisfies y prime equals y minus 1 over x squared with g of 2 equals 4. Okay, write an equation for the line tangent to g at 2, 4. This sounds really easy, okay, because I've got the point already. I've got a formula for the slope. Y prime is going to be equal to, okay, y minus 1 is 4 minus 1 over 2 squared is 4. That's looking like 3/4. So I'm ready to write a tangent line. Okay, y minus 4 is equal to 3/4 of x minus 2. It's great. Okay, that one was a really easy question. These are the types of things that they usually will start you off with on the free response question. You know, let you get a couple points easily, and then ask you something a little more difficult. All right. Now, then they ask, does the tangent you wrote in part A lie above or below the graph of G? Now, this is something we haven't talked about yet. Tangent is above the curve or tangent is below the curve. But what I will tell you, those of y'all sitting here, is some people take whether the tangent lies above or below the curve as the definition of concavity. So what we need to do is we need to consider the second derivative, the sine of the second derivative, and then we'll look at, you know, the tangent line and see if it's above or below. So if you're, you know, sitting at home, you're like, okay, I don't really see what you're talking about. What I'll do is I'll draw something that's definitely concave up, and then I'll draw a couple of tangent lines. Okay, well, that was tangent line below the curve. How about over here? Tangent line below the curve, even though it was not a very good line. Okay, then, you know, maybe in the middle. What do you know? Tangent line below the curve. Okay, meanwhile, if we had, oh, no, that's concave up at the end. Okay, yeah, nice and concave down. Okay, so we look over here. Tangent is above the curve. Tangent is above the curve. Tangent is above the curve. Okay, so what we're going to do, I don't even recommend you memorize this rule. I think you just need to remember that the concavity is going to determine whether the tangent line lies above or below the curve. Okay, so let's start by just finding, you know, the second derivative. So I'm going to take the derivative of y prime. So the second derivative of y with respect to x both times is going to be, I'm going to use the quotient rule, bottom times the derivative of the top, minus the top times the derivative of the bottom, divided by the bottom squared. All right. Oh, yes, I remember, because in part A, we found that dy dx was 3/4, so that'll be something I can say. Okay, x squared is going to be 4 times 3/4. We'll make that 3. Minus, okay, y minus 1 is 3 times 4. Divided by 2 to the 4 is 16. All right, so I've got 3 minus 12 is negative 9 over 16, meaning the second derivative is negative. So g is concave down, and the tangent lies above the curve. And the reason I'll give is that the second derivative at the point 2, 4 is less than 0. Now, I'm already gone a little longer than I prefer these videos to be, but I'm going to do a couple of multiple choice problems before I finish. Okay, if 3x squared plus 2y squared, or 2xy plus y squared equals 2, I want the slope of the tangent at x equals 1. Well, I know that when I find dy dx, it's going to involve a y and an x. So I need to figure out what y is going to be. Okay, so right now I'm going to take x equals 1, and I'm going to plug it into the original equation to figure out what y is. Okay, 3 times 1 squared is 3, plus 2 times x times y, plus y squared equals 2. All right, well, I'm going to subtract 2 from both sides and kind of write it in a more sensible order. And then I'm going to factor the thing. And I'll conclude that y is only -1. Okay, so there's only one place where this happens, which makes sense. I'm saying the value of dy dx. So now I've got the y coordinate. I can go ahead and take the derivative. Okay, 3x squared, that's 6x, plus 2 times, okay, the derivative of xy, take the derivative of x, leave y the same, then leave x the same and take the derivative of y. Then take the derivative of y squared equal to 0. Okay, now I'm going to distribute the 2. Clear out everything that doesn't have a dy dx and factor out the dy dx. -6x minus 2y divided by 2x plus 2y. All right. And then I'm going to plug in x equals 1 and y equals -1. And I'll have, okay, -6 plus 2 is -4 divided by 2x plus 2y is 0. Okay, so I've got -4 divided by 0. Which answer choice should I choose? Yeah, not defined. -4 divided by 0, not a real number. So dy dx is not defined. That's pretty rare, right? Usually it's not, like, does not exist, or none of these, or whatever that last answer choice. And the last example I've got for you is kind of a nice one. Sine of x equals e to the y. What is dy dx in terms of x only? It's like, oh, that's interesting. So we probably could have done this problem a couple of units ago if you had just started by taking the log of both sides of the equation and saying y equals the log of sine of x and use the chain rule. That works. But I'm going to do this with an implicit derivative. What I'm going to do is I'm going to say, I'm going to take the derivative of both sides of this equation with respect to x. So that means that cosine x is the derivative of e to the y is e to the y, but the derivative of y is dy dx. So got to remember the chain. Okay, and meaning that dy dx is equal to cosine x over e to the y. But they want this in terms of x. So it's like, how am I going to get rid of this e to the y? Well, fortunately for us, they have a formula for e to the y. It's sine x. Okay, so you just make that quick substitution. And that's cosine of x divided by sine x. And we know that that's cotangent x.
Will they give you that formula? Or do you need it?
Are you talking about cosine over sine?
No, sine x equals y. I mean, y.
Yeah, that's in the statement of the question. In this particular case, sine of x does happen to equal e to the y. But, you know, yeah, they always give you enough information to solve the problem. All right, and I think that's all I got for you.